Okay, so hi everyone, I'm Sanjana and today I'm going to be taking a class on invariants and monovariants. So if at any point you want to ask something or you're not understanding what I'm saying, then please feel free to speak up. So let's start. So first, let's go over the definition of invariants. So invariants are basically a quantity which does not change. So if you have some sort of situation and a problem where you perform operations on something, and there's some particular quantity that does not change no matter what sort of operations you perform, assuming they're like allowed operations. So that's called an invariant. And invariants generally can come in very useful in Olympiad problems. And we'll see many applications and concepts today. So an example of an invariant is Euler's theorem and graph theory. So suppose you have a graph in which none of the edges intersect. So it's called a planar graph. So this theorem states that, so in case anyone is not clear about this, just please ask. So the theorem states that the number of vertices minus the number of edges plus the number of faces is equal to 2. So a face is just an area which is not cut by edges. So this is one face and this whole thing outside is another face. So here you have 4 minus 4 plus 2 is equal to 2 and it holds here. So the proof of this is suppose you have some big graph, then you can either do two things. Either you delete some edge and that's part of a cycle here. So you're removing this edge and you're also removing this face because this face becomes part of the outside face. So in this operation, edges decreases by 1 and faces also decreases by 1. So this thing remains constant. And also you can so now you have this, right? So also you can remove a vertex and the edge that is connected to it. So you just don't want to leave any edge hanging. So that's why you can just do these two types of things. So in this case, you're removing a vertex and you're removing an edge. So again, this remains the same. So you can kind of keep doing this until you just have, say, one vertex in which it's easy to show that it's 2. So in that way, you can show that it's constant. I know the proof isn't very formal. I just wanted to give you an idea. So this is a kind of good example of an invariant, something that doesn't change. So now let's do a very basic problem just so that you get the idea. I hope it's visible. Just tell me if you're not able to see it. So you can try this for a few minutes, and if you have any ideas, please speak up or put it in chat. It's your choice, but preferably speak up. I'll wait for 1 more minute. So if anyone has any ideas, please tell.
Shall I say it?
Yeah.
So if you see modulo 3, every time it increases by 2.
Yes, exactly.
So after 3 to the power whatever minutes, it would be 2 mod, 0 mod,
Yes.
0 mod 3. Not
Yeah.
possible.
So like if two people leave, yeah, if two people enter, then it's increasing by 2, which is so it's increasing by 2 mod 3. And like if one person leaves, then it's increasing by minus 1 mod 3, which is the same as this actually. So each time it's just changing, like increasing by 2 mod 3. So after these many minutes, it will have increased by 2 mod 3 times this multiple of 3. So like the number of people in the room will be a multiple of 3. Right, so it can't be this because this is 1 mod 3 and you have something which is 0 mod 3. So yeah, that's the idea. Let's do one more easy problem. So you can try this for like 5 minutes and tell any ideas that you have. Okay, so think about what happens each time. Like what happens to the number of marbles of each color each time you do something. Yeah, okay. Can you explain why it's blue?
Shall I say it?
Okay.
So every time, if you look modulo 2, the blue marbles, like blue marbles either reduce by 0 or they reduce by 2. So blue marbles
Yeah.
remain constant modulo 2.
Yes. So the number of blue marbles either like it changes only by 0 modulo 2. So by the end, like so initially you have an odd number of blue marbles, which is 99. So at the end, if there's only one marble, it has to be blue. So that's how you get it. So like here, basically we use the concept of parity, like 1 mod 2 or 0 modulo 2. So parity is like a very common concept in invariance. So this is like very common problem in invariance which involves parity. It's like you have integers 1, 2 to n written on a board, and here n is odd. And each step you take two numbers a and b, and you replace them with modulus of a minus b, so the positive value of the difference. And then you ask like what's the parity of the final number that you have. So right here also, what you do is if you're replacing two odd numbers with the difference, then like the difference is even. So you're like taking away something that's even because odd plus odd is even, and you're putting back against something that's even. Similarly, if both of these are even, also the sum is even and the difference is even. And if one is even and one is odd, then the sum is odd and the difference is also odd. So the parity of the entire thing on the board, like the sum of all the numbers on the board, does not change. So like the parity of the last remaining number is the same as the parity of the original sum. So that would be 2n into 2n plus 1 by 2. And here this is obviously odd and n is also odd. So your answer is odd. So this is like a very common problem that I just wanted to mention. So now I'll define monovariants, and then we'll do some problems on that. So monovariants are sort of similar to invariants, but the thing is they can like change in one direction. So they can either increase or decrease. So like you can also think of it as this way. So like suppose you have a sequence of things A1, A2, A3, and this A is your monovariant. Then you can have like AI is either less than or equal to AI plus 1, or AI is greater than or equal to AI plus 1. Like this is the general thing. So it's either like not increasing or not decreasing. But the thing is, you can also have special cases. Like you can have when it's strictly increasing and strictly decreasing, and you can use those special cases in proving things in problems. And so a lot of problems ask whether it's possible to do something. And those kind of problems, like if the answer is no, then usually you use monovariants to prove that. So if you're asked like whether it's possible to get from A to B and B is greater than A, but A is some monovariant that can only decrease, then you know it's not possible to do this. So there are many problems in which monovariants are applied in that way. So let's do one such problem. So you can try this one. So like in this, infected is just like a thing that happens to a square. You can also think of it as like coloring the square. So just say if you have any ideas. So like this one is mainly about picking the right sort of invariant. So just think about what possible invariants you have in this.
Okay, so like this is similar to chip firing game.
Okay, so do you know how to do this?
Like in chip firing game, you know that mostly like say some cell is infected, and we just take the square of the no, like we give cell these numbers, okay, and then we take just the square of these number. So most of these times these numbers are either monovariant or something, but like it will
Okay.
not it will not be a monovariant here since like it's just similar to a chip firing game, but it is not a chip firing game.
Okay.
Okay, so like I guess it's not possible, and maybe you can give a coloring argument.
Yeah, you're right that it's not possible. So do you have a proof?
Okay, so like some invariant and coloring argument would work, I guess.
Yeah, it's actually like a monovariant. But yeah, right idea.
What's the monovariant by the way?
If I tell that, then it'll kind of be obvious. But like, see, this is like a 2D thing. It's a grid. So there are not many options you can pick from. There are only like two options, and one of them obviously doesn't work. So it's the other. Yeah, come here, you can speak.
I think it's not possible.
Okay. Can you say how?
You just mentioned about it being 2D. So if you think of it as perimeter of all
Yes,
the
yes.
infected squares, so it's like the two infected neighbor becomes infected. This perimeter then gets constant when the third square Oh, I'm not able to frame it. Can you? Yeah.
Yeah, your idea is exactly correct. So like you have several cases. So suppose in one case, just two of them are infected.
Yeah, like the infected cells can't get out of the perimeter they have. She's saying,
Yeah,
right?
like the
It's just
total
yes,
perimeter
yes.
cannot increase basically. So if
Yes.
you have just two here, then your original perimeter is 8. And then when this also becomes infected, if you see it's still 8.
It's kind of
Similarly,
similar to like 1996 C6. It is that chip firing game you do in invariance and monovariants.
okay, nice. So yeah, so that's one case. And then another case is if these two are infected and then this becomes infected. So like in that case, it's also like it's originally 8 and it goes to 8 again. Now suppose three things are infected already. So here the original perimeter is 12. And when you add this as well, you're like losing these three edges but getting this edge. So it becomes -2, which is 10. And lastly, if all four are originally infected, then it's 16. And then when this becomes infected, you're losing 4 edges, so it becomes 12. So like the idea you said is exactly correct. It's like the total perimeter cannot increase. Now you just use that to show that it's not possible. So basically the initial perimeter, if you look at the initial perimeter of the infected squares, you have 9. So the maximum is like if they're not touching, then the maximum perimeter you can have is 36. And you want it to become the entire grid, which is like 10 into 4, so 40. But here it's not possible because 40 is greater than 36 and this thing cannot increase. So that's how you prove it. So let's do one more problem. So I think this might be kind of similar to the chip firing game you mentioned, Anurag. So like if you know the way to do it, just don't tell now itself. Like if no one gets it, you can tell after like 5 minutes.
Oh yeah.
Okay.
What?
So does anyone else have any ideas for this? If not, then Anurag, you can tell.
I think it's not possible, but I'm not able to think of the reason behind it.
Okay.
It has to increase, like, you cannot get the same configuration.
Yeah, it's kind of intuitive, it's not possible. You can kind of say like the farthest thing is only moving further, but it's not really a formal thing. Like I kind of want you to try this with like finding an invariant and then using it. So like I will give you like 2 more minutes. So if you don't get anything, then Anurag can tell, I guess. Okay, so any ideas? Okay, so the idea is to find an invariant which is a monovariant, which like only increases or only decreases. So then you can say that you can't return to the starting configuration because it obviously can't come back to itself. So like the answer is kind of simple, but try to do this with motivation. So like suppose this is your strip of squares and you have your students. So since there's like nothing numerical in this, a thing you can do is assign weights to things. Like that's a common idea in invariant problems. So there are two things you can do. You can either assign weights to the squares or you can assign weights to the stones. Now the problem is if you assign weights to the squares, so like if you have some number of stones here or here, then it doesn't really make a difference. Like the weight you have is kind of still the same, right? But the squares are different, and you kind of want to incorporate that because that sort of matters in the problem, like which square is placed where. So it might be a better idea to assign weights to the stones. So suppose you're just starting out and you assign the like you suppose you number the squares and then you assign weights like according to the square on which it is on. So like here you'll have 4 and 4, and then suppose you move it will have 3 and 5. So like you can't really have an invariant with that because if you take the sum, it's just it's the same, right? So you need something that changes. So a kind of smart thing to do would be to take the square. Because initially, suppose you have k and k, and then you have k minus 1 and k plus 1. If you notice, like if you take the sum of the squares, here you have 2k square. But if you take the sum of these two, then you get 2k square plus 2. So basically your invariant is the sum of the squares of the number of the number of the square on which a stone is. So like if the stone is on square k, its weight is k square. And you just sum all of them and you get that they're increasing, like the value is increasing. So that's why it's not possible to return to the starting configuration. So like in general, a lot of invariant or monovariant problems ask if it's possible to do something. So in most cases, the answer is no, because if it's yes, then you can't really use invariants or monovariants. So there are like many types of problems in which you can use them. So in one case, you're asked if you can get from A to B, like how I mentioned earlier. And like either A is increasing and B is less than A, or A is decreasing and B is greater than A. So if you can find that kind of a monovariant, then you can prove that it's not possible. And the kind of thing we saw just now is it possible to get from A back to A? So in this case, you need a monovariant that definitely changes just in one direction, like the one we found. So then it's clearly not possible to do this. Another kind of problem would be like, is it possible to do something for like an infinite number of moves? So what you can do here is you find some sort of monovariant that is like definitely increasing or decreasing. But then you also find some bound based on the conditions in the problem. So then if there's a bound, then this monovariant can't keep increasing. So this thing has to stop at some point. So that's also an idea you can use. So now let's try a slightly harder problem. If in case you've seen it before, just wait for a few minutes before telling your solution. So I hope the problem is clear to everyone. Just tell me if it's not. So you can try this for like 5 to 7 minutes. Like all the coefficients are positive, like non-negative, right? Yeah, okay. So does anyone have any ideas? Like Archit and Malay, if you guys have ideas, you can also tell.
Should I say it?
Okay.
Yeah, I think it's good to look at the coefficient of x to the power 36.
Yes. So what you do is you basically just figure it out and like see what happens. So like suppose you have some two polynomials, say this and this. Now suppose you do the addition thing first. So you replace them with two more. So like here, obviously the x to the power 36 coefficient, that's a plus b, but it's also equal to c plus d. Like if you're adding, they obviously have to be equal. Now suppose you multiply. So like the product is the same. So even in this case, what you do is you look at the coefficient of x to the power 73. So like the product thing you get is this plus, in this case, you have a plus b x to the power 73, because you can only get it like either from like this and this, or this and this. So it has to be a plus b. But similarly, because of the second thing, you're replacing those two with, it also has to be c plus d. So like a plus b is always equal to c plus d. So because of that, you can see that the coefficients, the sum of the coefficients of the x raised to 36 term, that sum is invariant. So after that, it becomes kind of easy. So, so suppose you have like this sum, let's just call it k or something. So initially, you know that all the coefficients are non-negative. So this k has to be non-negative. So no matter how you change the polynomials, there should always be some polynomial with the coefficient of x raised to 36 as non-negative, because otherwise like the sum won't be non-negative. So if this coefficient is non-negative, by Vieta's relation, you have that like the sum of the roots, it's called as m. So like the sum of the roots is equal to minus m. So, but if all the roots are positive, then all of these m's, they'll be negative. So that's why it's not possible. So like if there's anyone who's not clear on Vieta's relations, please let me know, then I'll just explain that part. So I'm assuming it's fine for everyone. So now I'll give you another problem. And this is an ISL problem. So in case you've seen this before, you can tell me and I'll give you something else to try. So can you explain it? Can you speak? Can you explain?
Yeah, like just count the number of pairs x comma y, so that x is greater than y and x is to the left of y. And I
Yeah.
claim that if you are going to apply the operation infinitely often, this will eventually just become zero and then you can't perform any more operations. So that's a contradiction.
Yes, but like, okay, yeah, that
So
makes sense.
to prove that, like you can look at the maximum value and you'll observe that after finitely many iterations, the maximum value gets pushed to the very end and then it will never be used again. So,
Okay, yeah, that is a nice solution. There's also like a kind of different intended one, which uses an invariant. I mean, it's not that intuitive, so I'll just say it. So basically, the motivation is like initially you have x and y, and x is greater than y. And then you replace it by y plus 1 and x, or x minus 1 and x. So like here, this is less than or equal to this, and here this is less than this. So yeah, 1 second. Yeah, so like if you notice, like in general, if you have like something big into something small, and something else like small into big, or if you take like this big into big and small into small, then this thing is always greater, right? So like you can kind of use that to establish a monovariant here. So if anyone is not convinced by this, you can tell me. I mean, it's not that hard to prove. You can just put variables and like bash it out. But like, so what you want is like you want something. So this is big initially. So you want something small to be multiplied by this, and something big to be multiplied by this. And then when you have this kind of thing, then the small thing will be multiplied by the smaller thing, and the big thing will be multiplied by this bigger thing. So you can prove that the thing you get is greater than what you initially had. So a nice way to do that would be like to assign weights to the variables based on their positions. So if you have A1, A2 till AN as the numbers, then you can assign the weight as this number. So you can have A1 plus 2A2 plus so on till NAN. So then initially when you have this X and Y, that it like suppose they're at positions K and K plus 1. So then the value you have for that would be Kx plus K plus 1y, which is Kx plus Ky plus K. So now when you change it, let's take this case. So then you have Ky plus K plus K plus 1 into x. So you have Ky plus K plus Kx plus x. So if you compare these two, then you can see that Ky cancels, Kx cancels, and you have like K plus x and K. So obviously this is greater. Now suppose you take the other case. So you have K times x minus 1 plus K times x, K plus 1 times x. So that's Kx plus K. And then here you have this thing. So in this case also, if you work it out, you can see that this one will be greater than this. So that means that this total thing you have, that always increases. Now the problem is, as Archit said, the maximum term will remain the same. So if the maximum term remains the same, then you kind of have like an upper bound on this, right? So it can't go on increasing indefinitely. So that means that we can only perform finitely many operations here. So that's done.
That's a neat monovariant.
Yeah. Okay, so you can try this for like 7 minutes. Okay, so any ideas? Just kind of a tricky problem because like the main step is not obvious. Yes, that's the idea. So the invariant you want to use here is exponents, which is not a very common thing. That's why it's not really obvious. So here you have like n and n plus 1, and that gives n minus 2. And here you have n and n plus 4, and that gives n minus 1. So what you'd like to have is some x such that x raised to n plus x raised to n plus 1 is equal to x raised to n plus 2, and x raised to n plus x raised to n plus 4 is equal to x raised to n minus 1. So, one second. Yeah, so what you do is you divide by like x raised to n minus 2 in the first case. So you get x raised to 2 plus x raised to 3 is equal to 1. And in the second case, you get x raised to, you get x plus x raised to 5 is equal to 1. So basically you have two polynomials and you want something that satisfies both of them. And in this case, you're kind of lucky, or it's actually because the problem is phrased that way. So this is actually a multiple of this, like this is a factor. If you divide it, you'll get another polynomial. So once you do that, you know that if you pick something that satisfies this, it also satisfies this. So like both of these are 0. So let's consider some such x, and you're basically taking everything, like you're taking x to the power n, and you're taking the sum for all n in your set. So what you get is, so like let's call the set L. So the sum of x raised to n for all n and L. So you want to like kind of find some bound on this because you're asking for the most negative integer. So if you get a bound, that will kind of be nice, right? So you know that this is less than sum of x raised to n for all integers, like for all natural numbers, right? And this thing is kind of nice to compute because like suppose you have the sum, then you have this, and you can write it as, if you multiply it by x, you get this. This is like classic summing of infinite series. So you get 1 minus x s is equal to x if you subtract. And now you have s is equal to x by 1 minus x. And you also have that x raised to 5 plus x is equal to 1. So x raised to 5 is equal to 1 minus x. So if you just put x raised to 5 here, you get x raised to minus 4. And like, let's take the most negative integer you have in this. So let's let it be k. So like, let it be minus k. So x raised to minus k is like, let it be k. So x raised to k is obviously less than this, right? So you have that x raised to k is less than x raised to minus 4. And obviously x is less than 1 because of this. So let the reciprocal of x be y. So then you have y raised to minus k is less than y raised to 4. So minus k is less than 4 and k is greater than minus 4. So now you can try to prove that it works for minus 3. And that's kind of easy because if you just have 1, 2, 3, 4, and 5, and you do like almost anything, you get minus 3 as one of the values. So like you get minus 3 eventually. So you're done in that case.
Oh, this
So
was nice.
yeah. So I'll give you one more problem. So this one solution is kind of long, so I won't give the whole solution. I'll just tell you like the main steps. But you can try this for like 6-7 minutes. Yeah, so that's the idea. So like basically you have that x comma y goes to like this and this. So negative weights is kind of like a natural thing to think of here. So if you have, because like 1 by 2 to the power x plus y is equal to like 2 times 1 by 2 to the power x plus y plus 1. So you just take the sum of the coordinates and you do 1 divided by 2 to the power of that. So what you have to do for the bounding is like you first figure out what happens, like the thing you have initially, which is an invariant. So you get that as like 11 by 16. And now you assume that you have cleared all of those squares. So let's say that you have in the maximum scenario, you have counters on all of these. Like you have tokens on all of these. So you have to prove that like even in that case, the sum is less than this. So what you do is like first you find the sum of everything, like the value if there were tokens on everything, and then you subtract 11 by 16, and then you'll get something that's less than 11 by 16. But obviously you can't get that because this is invariant. So you're done. The only kind of tricky part is like doing the infinite summation, but that's not that hard. So just I think you should be able to do it. So yeah, that's it for today. I hope you understood. If there's anything you want to ask, you can like stay back. Otherwise you can leave, I guess. Thank you.
Should I stop the recording?
Yeah, you can stop.